You see a jet pointing toward the sun, not away like every comet you know, toward it. 6,200 miles of gas and dust blasting sunward from a visitor that came from another star system. The image drops October 15th, 2025, from the 2-meter twin telescope in the Canary Islands, and every astronomer with a screen sees the same thing. Purple line, Sunward. The comet sits behind our sun right now where we cannot watch it, and some people think that matters. The jet matters more. Speed, 61 kilometers per second relative to our star. The object moves along the border between Serpens Cauda and Sagittarius near the galactic plane, and within hours, follow-up observations start flooding in from observatories worldwide. Zwicky Transient Facility finds pre-discovery images from June 28th and 29th. More images from June 14th to 21st. Atlas itself has captures from June 25th to 29th. Amateur astronomer Sam Dean digs deeper and locates Atlas observations, going back to June 5th through June 25th. Nobody caught it earlier because it passed in front of the galactic center's dense star fields, where one faint comet disappears into a million background lights. July 2nd, 2025 changes everything. The Deep Random Survey in Chile spots a marginal coma with potential tail elongation measuring 3 arcseconds. Lowell Discovery Telescope in Arizona confirms it. Canada, France, Hawaii Telescope at Mauna Kea sees the same feature. David Jewett and Jane Liu use the Nordic Optical Telescope and confirm the object is clearly active with diffuse appearance. Miguel Alarcón and his team at Instituto de Astrofísica de Canarias use the 2-meter twin telescope at Tidy Observatory and find cometary activity that same date. The Minor Planet Center announces the discovery and assigns the designation 3, I meaning third, confirmed interstellar object after 1, I Oumuamua from 2017, and 2, I Borisov from 2019. The comet also gets the non-periodic designation C/2025N1 Atlas. By announcement time, the MPC has collected 122 observations from 31 different observatories. July 21st, 2025. The Hubble Space Telescope images. 3I Atlas, when the comet sits 277 million miles from Earth at 3.8 astronomical units from the Sun. The image shows a teardrop-shaped cocoon of dust coming off the solid, icy nucleus. Background stars streak because Hubble tracks the comet moving along its hyperbolic trajectory. The image reveals something else. Extended glow pointed toward the sun. The viewing direction aligns within only 10 degrees of the line connecting 3I Atlas to the sun. This geometric fact means we see the extension nearly edge-on. The glow appears twice as long toward the sun as it does perpendicular or opposite, but the 10-degree viewing angle creates a projection effect. The geometric correction factor equals 1 divided by sine of 10 degrees, which gives 5.76. If you hover above this elongated glow perpendicular to the sunward direction, you would see it extending 10 times farther toward the sun than its width or tail. Solar radiation pressure and solar wind push dust and gas away from the sun. Every familiar comet shows a tail streaming opposite to the sun. 3I Atlas shows an anti-tail, real physical feature, not optical illusion. The only previous anti-tails on record, like Comet Kohoutek from 1974, result from perspective geometry when Earth's position creates the appearance of sunward extension. Those are false anti-tails. 3. I Atlas displays the real thing when it sits far from the sun, moving toward both Earth and the sun with a genuine sunward jet visible even at unfavorable projection angle. Also comment from which city you're hearing this from. This script is researched and factual using sources from the Arxiv preprint server, specifically paper 2510.18.157 by Eric Quito and Abraham Loeb from the Harvard University Department of Astronomy, published October 23rd, 2025, analyzing Hubble. Space telescope observations and physical models of ice coma evolution, plus the astronomer's telegram bulletin posted October 15th, 2025, documenting the 2-meter twin telescope observations with 159 exposures captured August 2nd. Now back to the information. August 2nd, 2025. The 2-meter twin telescope captures 159 exposures of 50 seconds each, totaling over 2 hours of observation time. The composite image shows the dark nucleus as prominent central dot surrounded by luminous white coma, which is the cloud of gas and icy dust. A distinctive fan-shaped disruption reveals where the jet originates, extending approximately 6,200 miles or 10,000 kilometers from the surface, oriented precisely toward the sun, aligned with the comet's velocity vector. Astrophysicist Michael Serra-Ricard, Chief Science Officer at Lightbridge's research institution that co-manages TIDA observatory, posts the images October 15th. Serra-Ricard states this is the usual. Jets are pointing to the sunward direction and the comet's tail in the antisolar direction. The 2-meter twin telescope observation confirms what Hubble saw in July. Sunward jet extending 6,000 kilometers from nucleus, not 6,000 kilometers total. 6,000 from the crossing point of the red lines marking nucleus position outward toward the sun. The purple line in the processed image marks the jet direction. Yellow line shows antisolar direction where normal comet tail should point. Blue line indicates velocity vector. The jet shoots sunward. The measurements match. Hubble in July showed projected distance around 6,000 kilometers accounting for viewing angle. TIDA in August shows the same 6,000 kilometer extension. 2 independent observations, 2 months apart, same feature, same scale. Very large. Telescope observations from July to August 2025 detect elevated cyanide and nickel emissions without iron mirroring concentrations seen in solar system comets. James Webb Space Telescope observations. August 6th, with near-infrared spectrograph instrument show unusually rich carbon dioxide content with small amounts of water, ice water, vapor, carbon monoxide, and carbonyl sulfide. SphereX Space Observatory observations. August 8th through 12th, when 3I Atlas sits 3.2 astronomical units from Sun and 2.6 from Earth, reveal carbon dioxide cloud extending to at least 348,000 kilometers, corresponding to mass loss rate about 70 kilograms per second, no water cloud detected, upper limit 4.5 kilograms per second on water mass loss rate. This is order of magnitude below earlier water detection claims. The jet comprises primarily dust particles several micrometers in radius and carbon dioxide gas, with coma's reddish hue from irradiated organic compounds called tholins, matching compositions, in solar system comets and previous interstellar comet 2 I Borisov. Harvard astronomers Avi Loeb and Eric Quito published analysis September 10th in Archive paper explaining the anti-tail mechanism. The glow around 3I Atlas stems from scattering of sunlight by ice fragments, shed from surface rather than refractory dust particles. Most scattering comes from ice grains with size comparable to wavelength of sunlight about half a micrometer. The ice fragments evaporate after some time, but enhanced mass loss on sun-facing side allows bigger fragments to reach large distance, giving rise to anti-tail. The anti-tail represents extension of snowline or survival distance of sublimating ice grain in direction of sun. The longest surviving grains are mostly water ice, which evaporates more slowly than carbon dioxide ice. Surface temperature responds quickly to illumination angle because rotation is slow enough. Mass flux from sunward surface exceeds that from rest of comet by factor sufficient to produce observed sunward elongation. The mass flux determines both terminal velocity of ice grains and maximum size and grain size distribution, therefore characteristic survival length of ice grains in outflow. Small dust grains with 1 micrometer radii get ejected from nucleus at fast speeds of 22 meters per second. Large dust grains with 100 micrometer radii get ejected at slower speeds, about 2 meters per second. Water ice grains with around half micrometer size scatter sunlight most effectively and survive long enough to extend sunward when launched by carbon dioxide sublimation drag. As comet nears sun, the exponential temperature dependence of sublimation rate causes continuous increase in production rate of ice grains and sharp decline in their residence time and outflow. Combined effects produce peak in total scattering cross-section due to water ice grains at distance of 3 to 4 astronomical units from sun. At closer heliocentric distances, scattering becomes dominated by longer-lived refractory dust particles and larger volatile grains with survival times long enough to form tail stretching away from sun. This explains what happens next. Nordic Optical Telescope observations through September show transition from anti-tail to conventional tail. Images from 2.5 meter diameter telescope in Canary Islands reveal evolution. July shows pronounced sunward anti-tail. August continues showing sunward extension. September shows reduction in anti-tail and growth of tail in direction away from sun. Keck telescope observations reported late September confirm the shift. Gemini South Observatory observations by end of August show anti-solar tail has become more visible and grown to 30 arc seconds, angular length or roughly 56,000 kilometers. By September 15th, 3I Atlas displays visible dust tail length of 50 arc seconds, approximately 100,000 kilometers pointing away from sun. Quito and Loeb published detailed theoretical model October 23rd in Archive paper 2.510.18157, explaining transition physics. as 3. I-Atlas approaches Sun from 4 astronomical units down to 3, then 2. The equilibrium temperature of water ice grains becomes high enough that destruction by sublimation shortens residence time. Total scattering cross-section of water ice grains peaks at distances between 3 and 4 astronomical units. Closer than 3 astronomical units, refractory dust dominates, tail flips, anti-tail disappears, normal comet tail emerges. The model matches observations perfectly. Jewett and Liu document the evolution in Nordic optical telescope images, showing brightest pixel marked by red dot shifting position as coma morphology changes from July through September. Sunward is west in their images. Distance from Sun, expressed in astronomical units, decreases as comet approaches perihelion. The jet seen August 2nd by 2-meter twin telescope captures 3I Atlas during peak anti-tail phase when water ice grain scattering dominates at 3.2 to 3.5 astronomical units from Sun. This is exactly where Keto Loeb model predicts maximum sunward extension. The 159 exposures of 50 seconds each provide high signal-to-noise composite revealing jet structure, fan-shaped extending from nucleus. Processing by teams at NOIR and Aura enhances faint features. Gemini North Telescope provides wide field background view, showing comet position among star fields. Tidy observatory data highlights jet details. Result is one of most detailed ground-based views ever obtained of interstellar comet, displaying active jetting behavior. The mass loss tells the story. From July to October 3, I-Atlas loses approximately 2 million tons of material. This equals 0.00005% of total mass estimated at 33 billion tons by Loeb and colleagues based on Sphere X observations. The Sphere X images show 3I Atlas as point source with no resolved dust coma, implying glow around object in Hubble. Image is compact corresponding to small dust amount. The flux detected by Sphere X at 1 micrometer wavelength suggests even larger nucleus diameter of 46 kilometers. This mass is million times larger than previous interstellar comet 2 I Borisov and million times larger than 1 I Oumuamua. The huge gap surprises astronomers. We should have discovered numerous object size of 2 I Borisov before discovering 46-kilometer interstellar object. The amount of rocky material per unit volume in interstellar space is smaller by a factor of 10,000 than value needed to deliver into inner solar system one giant rock this size over decade-long Atlas survey. Hubble observations constrain nucleus diameter between 320 meters and 5.6 kilometers, with most likely diameter less than 1 kilometer. The large uncertainty exists because nucleus is surrounded by coma of reflective dust, making it appear brighter and larger than actual size. Early studies from July gave diameter estimates as high as 10 to 20 kilometers, but astronomers were aware nucleus should be much smaller. Estimated dust loss rate suggests nucleus likely less than 1 kilometer diameter, similar to 2 I Borisov. The coma brightness accounts for a large fraction of apparent brightness, so actual nucleus diameter should be at lower end of estimated range. October 3rd, 2025. 3I Atlas passes Mars at distance close enough that European Space Agency's Mars orbiters, ExoMars and Mars Express, capture images. The observation is very challenging for cameras because Comet is about 10,000 to 100,000 times fainter than usual targets, which are bright Martian surface fewer than 200 miles below. Comet sits 18.6 million miles away from orbiters when images are taken. Nick Thomas, principal investigator of CAS's camera, states scientists were unsure what to expect from observations of relatively dim targets so far away. The cameras designed to photograph Mars succeed in capturing interstellar visitor, providing unique perspective from red planet. October 21st, 2025. 3. I-Atlas reaches solar conjunction, sitting exactly on opposite side of Sun relative to Earth. The comet becomes unobservable from Earth-based telescopes. GOES 19. Weather satellite potentially observes comet during conjunction from its position. October 29th, 2025. 3I Atlas reaches perihelion at distance of 1.36 astronomical units, or 203 million kilometers from Sun. This is between orbits of Earth and Mars. The comet passes under the Sun, where we cannot see it, where some speculate it might do things we cannot observe. Avi Loeb suggests, if 3I Atlas were spacecraft, most energy-efficient moment for engine burn is at perihelion due to Oberth effect. Firing engine, when orbital velocity is greatest, maximizes gain or loss of kinetic energy. If Comet is massive mothership, Oberth maneuver might apply to mini-probes. It releases at perihelion towards solar system planets. November 4th, 2025. ESA's Jupiter Icy Moons explorer called JUICE passes within 64 million kilometers from 3I Atlas. If comet maintains trajectory shaped by gravity only, it reaches closest approach to Earth, December 19th at distance of 269 million kilometers, or 1.8 astronomical units. March 16th, 2026. 3. I-Atlas passes within 54 million kilometers from Jupiter, observable to sensors in ultraviolet infrared and radio bands aboard Juno spacecraft. Spacecraft Hera predicted to be immersed within ion tail of 3 I-Atlas during period October 25th through November 1st, 2025. Hubble July 21st shows 2-to-1 projected elongation, correcting to 10-to-1 actual elongation pointing towards Sun. TIDA August 2nd shows fan-shaped jet extending 6,000 kilometers sunward. Nordic Optical Telescope through September documents transition from anti-tail to normal tail as distance from Sun decreases below 3 astronomical units. Keto Lobe model published October 23rd explains mechanism through water ice grain, scattering driven by carbon dioxide sublimation, with peak scattering at 3 to 4 astronomical units, followed by dust-dominated tail closer to Sun. Sphere-X August observations confirm carbon dioxide dominance with 70 kilograms per second mass loss and minimal water. Very Large Telescope detects cyanide and nickel emissions. Webb Telescope reveals carbon dioxide-rich composition. Every observation from 6 different major observatories matches the ice grain scattering model. Carbon dioxide sublimation on sun-facing hemisphere launches water ice grains at sufficient velocity that largest grains survive long enough to scatter sunlight at distances extending 6,000 kilometers towards Sun before evaporating. The projection geometry makes it appear as 2-to-1 elongation, but actual 3-dimensional structure is 10-to-1 jet. As comet approaches from 4 astronomical units to 3 to 2, the peak scattering shifts from water ice to refractory dust and volatile grains that form conventional tail. The transition happens exactly when and where Keto Lobe model predicts. The August 2nd TIDY observation captures jet during peak phase. The Hubble July 21st image captures earlier phase at 3.8 astronomical units. The Nordic September images capture later phase showing tail emergence. Sarah Ricard at TIDA states this is usual behavior but misses the point. Normal comets show jets pointing various directions, including sunward, due to uneven heating and geyser-like outbursts from weak spots in crust. Normal comets do not show 10-to-1 elongated jets pointing sunward, visible in projection as 2-to-1 features at unfavorable viewing angles. Normal comets do not require paper by Harvard astronomers explaining why water ice grain scattering driven by carbon dioxide sublimation produces anti-tail that transitions to normal tail that predicted heliocentric distance. 3. I-Atlas behaves like comet but displays morphology requiring new physical model to explain. Most solar system comets show roughly equal amounts of carbon dioxide and water, or water dominates. 3I Atlas shows carbon dioxide dominating by a factor of 15 to 20 over water. The surface composition shows mix of water and carbon dioxide ices combined with organics consistent with Kuiper belt objects exposed to interstellar cosmic rays. The coma exhibits unusually high degree of negative polarization at small phase angles based on Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory observations from July and August. Negative polarization means large percent of reflected light has oscillations oriented along Sun-comet observer plane. This suggests coma made of mixture of icy and dark material similar to trans-Neptunian objects. If you value this level of research and documented observations, subscribe to support the work. Comment which city you're watching from. This script uses detailed peer-reviewed and preprint sources including Nature Astronomy submissions, Astrophysical Journal letters, papers, and Arxiv submissions, specifically focusing on the October 23rd Keto Lobe theoretical model paper and August Sphere-X mission observations, published by C. M. Lisa and team from California Institute of Technology, showing carbon dioxide, cloud mass loss rates, and absence of detected water cloud. Back to the evidence. 3 I-Atlas enters inner solar system at 61 kilometers per second on hyperbolic orbit, with eccentricity greater than 1, meaning it is not bound to Sun and will exit solar system after perihelion passage. The trajectory aligns within 5 degrees of ecliptic plane of planets around Sun. This alignment has chance probability of 1/5 of percent, or 0.2%. Most interstellar objects should approach from random directions in 3-dimensional space. 3 I-Atlas approaches nearly in plane of solar system. The arrival time allows it to pass within tens of millions of kilometers from Mars, Venus, and Jupiter and be unobservable from Earth at perihelion. The direction of approach coincides within 9 degrees of direction of WOW signal detected August 15, 1977 from region near Chi Sagittarii. These are the anomalies Loeb catalogs in ranking 3I Atlas at 4 on Loeb scale. The jet does not make list of anomalies originally, but becomes anomaly when analyzed. Comets showing sunward features typically display either false anti-tails from perspective geometry or transient jets from specific active regions on rotating nucleus. Comet Kohoutek in 1974 showed anti-tail that was perspective illusion. Comet Neowise in 2020 showed sunward jets from active spots visible in Hubble images. 3I Atlas shows persistent elongated sunward feature visible across multiple observations from July through August, requiring specific physical model to explain. The jet requires carbon dioxide-driven sublimation launching water ice grains at precise size distribution and velocity distribution to produce observed 10-to-1 elongation at 3 to 4 astronomical unit distance with subsequent transition to normal tail closer to Sun. This is not standard comet behavior. This is comet behavior requiring new model. Hopkins and colleagues calculate 3I Atlas has 67% chance of being more than 7.6 billion years old. Our Sun and solar system and its comets are 4.6 billion years old. 3I Atlas could predate solar system by 3 billion years. If comet originated from Milky Way thick disk rather than thin disk, it could be at least 7 billion years old, older than solar system. The comet spent billions of years in interstellar space traveling through region, where stellar nurseries and stars provided gravitational slingshot effects increasing momentum. Speed of 61 kilometers per second relative to Sun makes it fastest interstellar object ever observed in our solar system, faster than Oumuamua, faster than Borisov. Pre-discovery observations go back to May 21st from Weizmann Astrophysical Observatory. TESS observed 3I Atlas from May 7th to June 3rd, when comet was roughly 6.4 astronomical units from Sun, showing it was already bright and active. This indicates activity likely caused by sublimation of volatile ices other than water, since water ice typically does not sublimate significantly beyond 5 astronomical units. Carbon dioxide, carbon monoxide, and other supervolatiles sublimate at larger distances. Vera Rubin. Observatory pre-discovery observations showed coma diameter grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. The object was not discovered earlier because it passed through dense star fields of galactic center, where one faint moving object is nearly impossible to distinguish from millions of background stars. For the anti-tail mechanism to work, nucleus must rotate slowly enough that surface temperature responds quickly to illumination angle, so mass flux from sunward surface exceeds that from rest of comet by sufficient factor. If nucleus rotates rapidly, surface temperature averages out reducing difference between sunlit and dark sides. 3I Atlas displays properties consistent with slow rotation, allowing sharp temperature gradients between illuminated and shadowed regions, driving asymmetric carbon dioxide sublimation that launches water ice grains, preferentially from sun-facing hemisphere. The jets from nucleus require active fraction of surface of only few percent based on observed mass loss rates. Most of nucleus remains inactive. The active regions concentrate on sunward hemisphere, where solar heating drives sublimation. Nucleus estimated less than 1 kilometer diameter. Coma extending 13,000 to 18,000 kilometers diameter in July, growing to much larger in August and September. Tail reaching 50,000 to 100,000 kilometers by September. Carbon dioxide cloud extending to 348,000 kilometers by August per spherex. All features grow as comet approaches Sun. Brightness increases, activity increases, mass loss increases from estimated 2 million tons, total between July and October. The object transforms from dim magnitude 18 at discovery to brighter as it nears perihelion, though never bright enough for naked eye observation. Telescopes worldwide track every change documenting evolution of third interstellar visitor in human history. Loeb suggests 30 to 40% chance of artificial origin, citing anomalies in trajectory, timing, mass, and behavior. If 3I Atlas were engineered probe, the sequence of events matches what one would expect for spacecraft, using Oberth maneuver at perihelion to either accelerate, decelerate, or release smaller probes. The Sunward jet could theoretically represent braking thrust from spacecraft slowing down, though this requires jet-producing thrust rather than being passive sublimation feature. Mainstream scientists strongly reject spacecraft hypothesis. Daryl Seligman at Michigan State emphasizes, this is only third interstellar comet we have been able to study, and planetary scientists are super excited to learn about what comets and other solar systems are like. Consensus holds JWST and VLT data affirm natural comet traits with no evidence of artificial construction or propulsion. If strange jet reversals and brightness patterns persist, defying natural explanation, the anomalous nature increases. November and December 2025 provide opportunity to monitor sky, searching for unusual activity of 3I Atlas or any new objects that came out of it. The comet reappears from behind Sun mid-November when Earth-based observations resume. Astronomers will document whether conventional comet tail persists, whether brightness follows expected thermal curve, whether any fragments or secondary objects appear, whether trajectory remains purely gravitational or shows non-gravitational acceleration. Mars reconnaissance. Orbiter. High-rise camera images from October 2nd, when Mars passes near comet's position, should provide sideways view of glow with pixel resolution of 30 kilometers if images get released. Government shutdown may delay release, but data exists. If released, high-rise images would test Keto lobe model by showing ice coma structure from different viewing geometry than Earth-based observations. The model predicts specific brightness distribution as function of angle from Sun-comet line. High-rise from Mars, orbit provides different angle confirming or refuting predicted distribution. The International Asteroid Warning Network announces campaign from November 27th through January 27th, 2026, targeting 3I Atlas, to exercise capability of observing community to extract accurate astrometry. Comets present unique challenges for accurate astrometric measurements and orbit predictions. Cometary bodies are extended with morphological features like comas and tails that can systematically pull centroid measurements off central brightness peak, presenting challenges to estimate trajectories. IAWN holds workshop on techniques to correctly measure comet astrometry preparing for campaign. The campaign treats 3I Atlas as test case for planetary defense drill, practicing precise orbit predictions for future potentially hazardous objects. The jet image from August 2nd, posted October 15th to Astronomers Telegram by Sarah Ricard and team from Tidy Observatory, Light Bridges Institution, marks most detailed ground-based view of Sunward jet from interstellar comet. The 159 exposures combining to show fan-shaped feature extending 6,000 kilometers matches. Hubble's earlier view confirms persistence of anti-tail during approach phase, documents morphology at exact distance, where Keto lobe model predicts maximum water ice grain scattering. The image is not yet peer-reviewed, but methodology is standard. 2-meter twin telescope is established observatory with track record. Light Bridges is recognized research institution. Sarah Ricard is credentialed astrophysicist. The observation matches independent Hubble data from different instrument, different date, same feature, same scale. Grains with half-micrometer radius scatter visible light efficiently. Illumination angle affects sublimation rate, creating asymmetry. Sun-facing hemisphere sublimates faster, producing higher gas flux, launching bigger ice grains to greater distances before evaporation. This creates extension of snowline in sunward direction, visible as 10-to-1 elongation in 3 dimensions, appearing as 2-to-1 in projected Hubble image, and as 6,000-kilometer jet in TIDA image. As distance to Sun decreases below 3 astronomical units, water ice grain residence time drops due to increased sublimation temperature. Refractory dust and larger volatile grains with longer survival times dominate. Normal tail emerges, anti-tail fades. Transition occurs August through September, exactly as predicted. Multiple spacecraft, multiple viewing geometries, multiple wavelengths, all testing same physical model, all checking. Whether 3I Atlas behaves as extreme composition comet with carbon dioxide-driven water ice grain scattering anti-tail, or whether unexplained features emerge. The evidence available now through October 27th supports natural comet explanation with unusual but physically explainable morphology. The jet is real, the mechanism is understood, the model fits observations. The spacecraft hypothesis lacks supporting evidence beyond statistical arguments about trajectory and timing. When it emerges mid-November, we will see whether it brightened as expected, whether tail structure matches post-perihelion predictions, whether any surprise features appear. The 2-meter twin telescope image from August 2nd captures comet during approach phase, showing sunward jet at peak visibility at distance, where water ice grains scatter most effectively before transition to conventional tail. That image, that fan-shaped purple feature stretching 6,000 kilometers toward the sun, is the evidence that matters. Not speculation about alien probes, not anxiety about hidden maneuvers. The jet itself, the measurements, the wavelengths, the composition, the timeline, the transition, the model that explains it all. Read Section 5 for heliocentric distance dependence. The math is undergraduate level thermodynamics and radiative transfer, vapor pressure, Clausius-Clapeyron equation. Energy balance, Hertz-Knudsen formula. Stefan-Boltzmann law, nothing exotic. The physics of ice sublimation and grain scattering applied to specific composition and specific illumination geometry produces specific prediction that matches specific observation. That is science. That is the evidence that matters. The jet points sunward because carbon dioxide launches water ice that scatters light before evaporating. The jet transitions to normal tail because closer to sun, everything evaporates faster and dust dominates. The observations from Hubble July, Tidy August, Nordic September all match this explanation. 3. I-Atlas comes from another star system traveled billions of years through interstellar space, enters our solar system, and shows us comet behavior we have never documented before, requiring new model to understand. The model works. The jet is explained. The evidence closes. Mid-November. When 3 I-Atlas reappears, we will see what comes next. For now, the August 2nd image from Tidy Observatory shows 6,000 kilometers of sunward jet at 3.2 astronomical units from Sun, confirming Harvard model of ice grain dynamics, showing interstellar comet behaving like no solar system comet. We have seen, but behaving exactly as physics predicts when you have 87% carbon dioxide composition launching half-micrometer water ice grains from slow rotating nucleus with asymmetric illumination at the specific distance where grain survival length peaks. That is what the evidence shows. That is what matters.